you for coming. I know it's been a long day, and I know tomorrow is going to be another longer day. Who's looking forward for the after parties today? Yes? Yes? Who's enjoying Brussels? Good? All right, need to break the ice because I don't know you. This is the first time at FOSDEM, so I want to get to know you. All right, so first of all, this is who I am, and I'm going to apologize for those in the recording, especially because I move a lot, and I like moving a lot, so helps me deliver better, and I think so. I speak too fast, so let me know if I'm not pronouncing correctly. I'm Mexican. My primary language is Spanish, so I have a hard accent. Let me know if I'm not pronouncing anything or you don't understand what I'm saying. So I work for the Linux Foundation, hence the penguin. I am the general manager for Dronecode. Dronecode is a project within the Linux Foundation. We specialize in drone stuff. I am initially a contributor, so I'm not a business developer or a sales or marketing person, although I had to be trained in that because the position required it. But I was initially an individual contributor, and I'm still am. And that's one of the reasons why I'm here, because I actually need help, and that's kind of like the reason why I'm here, to recruit some of you. I've been working for more than 10 years in robotics. Some of my colleagues are here, so I say hi. I co-lead the Rosa Aerial Robotics work group. Has anyone here have been working with robotics at all before? Okay, like a quarter of you, nice. Anyone know about ROS? Good, all right. So there's an aerial robotics ROS community work group that I co-lead with Kimberly McGuire sitting right there. And then I also co-lead the Space Red Linux initiative that started last year, in which we're trying to build a Linux distribution that is certifiable for space. And we're working with a few companies, NASA included, and that's a really cool effort. Hopefully next year at FOSDEM in 2026, I get to talk about that. But today, we're going to be talking about drones. All right, so what is Dronecode? So we're an open source UAV ecosystem. Honestly, when you hear about a foundation, like an open source foundation, what is the first thing that comes to mind? Like anyone?
No money.
No money? Yes, that's a very good one. It's like the funding to the project, right? But it's a bit more than that. And sometimes some of the foundations miss the opportunity to tell that story. And I'm going to try to do a good job here, but this is like the second time I do it this time. So we're trying to be a neutral home for the open source projects. What does that mean? It means that any company within the ecosystem can contribute, even if they're competitors. And that causes a lot of challenges. We're here to promote open collaboration, open standards, open source, and accelerate the innovation in the industry. The robotics industry has been around for, I don't know, for longer than I've existed probably. But it's been very slowly moving towards commercialization, to the point where right now you see humanoid robots, and like they're famous with AI, but honestly, they're still kind of gimmicky. There's not real applications yet. Like I haven't seen one that works perfectly yet, or that has been deployed out there. Maybe I'm wrong. Raise your hands if I'm wrong. You know an example? No? All right. It's good that I'm still right about this. And we want to support commercial adoption of open source, which is the biggest thing here, because if there's no commercial adoption, there's no industry. If there's no industry, how are we going to fund this, right? Because initially, this is what we're trying to do here. We want to make sure that the projects continue to be alive. So what we form here is an ecosystem. So Dronecode sits at the center, but we have the open source projects. These are some examples. I'm going to talk about the rest in a little bit. We also have industry standards, which is like an open hardware project. Mavlink, which is the standard for communication, a protocol in which we can define the behavior of certain components of drones. We have industry members, so some of the companies that actually support us and actually contribute back. And industry associations like the Linux Foundation, the Open Source Robotics Alliance, which hosts ROS, and we work with them, or the OpenCV Alliance as well. So we try to put everything together and make sure that there's a concise industry, and then there's an effort, there's an effort that we're trying to push things forward together. Why am I telling you all of this? because like you just saw, not a lot of you know about drones, and I just wanted to give you a quick context into what's going on right here. We've been around since 2014, but the projects have been around since 2009. It's not something new. It's been around for a while. It actually was born out of ETH in Zurich, but it has grown tremendously out of that, to the point where I just pulled the analytics, and we have already 13,000 unique contributors over time. So even though I say we're a humble, small community, we're growing over time a lot, but we're still struggling with some of the things that will allow us to grow more, like CI. Just some more stats so you know exactly what's happening here. Almost 60 million lines of code distributed across all of the repositories, which are almost like 100 repositories. We have 20 companies that are supporting us, and we have the top 5 projects which are there. PX4, which is the firmware for drones. PIXOC, which is open hardware, the flight controllers that actually control the drones. MapLink, the message protocol that I was explaining. Map SDK, which is an SDK that allows you to talk MapLink, because MapLink is basically an XML protocol. So Map SDK is a wrapper on top of that helps you build APIs to control it. And Ground Control, which is a very interesting project based on Qt, and it's a mission planning software, or ground station, how we call it, which allows you to control the freaking drones, which is pretty cool. All right, so let's hope the internet works. 2009. This is where we started. And it's important that we see where we started. Has anyone heard about PIXOC before, or PX4? Yeah, just a few. So this is like, look at the machine. Like, that is actually an Intel NUC, like a very old Intel NUC. Those are parts put together from like off the shelf in an electronics store. There's nothing secret here. It's just like a lot of pieces that were put together from electronics that were already available at the time. And we started from there. We moved a little bit further in a few years because it was like basically a research platform. And as you can see, you have more stable flight now. It's still an ugly machine, but no GPS flights now. It's autonomous flights. We got plane detection, an onboard camera. So we started getting fancy and putting more features on top of this. I'm not going to play the whole video. I'm going to share the slides later so you can all see it at home. But this is one of my favorite videos that we have. This is actually came out in our developer event in 2022. Look at the configuration of this drone. Look at how it's going to be moving in different directions. This is an omnicopter. So PX4 allows you to fly the vehicles that you saw already, and then vehicles like this that have a non-traditional geometry and allow you to do this type of movement, this type of autonomy. So as you can imagine, this is going to bring a lot of complications, especially when you're trying to test things. These are some of the other applications. Walmart was using our firmware and our hardware to do delivery in the US. There's companies that do mission inspection, like Infra. This is a vertical and takeoff. It takes off with the propellers, and then it transitions as a fixed wing mid-air. This is a vehicle that has a very funny characteristic. The payload, the camera, is like a $100,000 camera. It's more expensive than the drone. So you got to make sure that that camera is going to be safe at the end of the day, right? So how do we actually ensure that? It's hard. It's actually hard. We have another vertical takeoff and landing. This actually is a really cool vehicle. They can configure it differently. This company is called Quantum Systems out of Germany. And we also support underwater vehicles. So how do we make it so that all of these freaking applications fit in the same firmware? How do we make it so that we can test those things? And how do we prove that we're safe? So the honest truth here is that we cannot guarantee that. We are only a humble open source project that we depend on their contributions. I'm not any authority to be able to test this. Like the FAA in the US actually runs tests for aviation companies to be able to guarantee the safety. You cannot expect a foundation to be able to do this. But what you can expect is us doing our best to the best of our ability to actually guarantee the safety to the best of our possibilities within our resources, because it's expensive. All right, so the answer on how do we do this is the PX4 Autopilot, the firmware. And this is going to be a little bit deep into the technical side, but I'm going to try to explain the functionality of the firmware so that I can finally go into the CI and testing and how do we do it. So we're running on top of the RTOS. Everyone knows what an RTOS is? A real-time operating system. All right, basically it's like a operating system that guarantees the execution of the commands whenever you say you wanted to do it, and it's a gross characterization, but it's like think of a fancy scheduler that guarantees that whatever you said is going to happen, happens. We're C++ based. We're modular, meaning that within the operating system, different components of the firmware actually run on different modules. Like think of different apps. Like the app that runs the logging is different from the app that runs the estimation or the control. And that's important because you don't want the logger to actually fail and then the drone is going to crash because the log is not working. That's not something that we want, so we want to make sure that it's separate. But how do we actually connect everything, like all the modules, through a middleware? Middleware is basically a publish and subscribe component of our system that actually just basically says, okay, this is the driver for the GPS, and this is the location that we're publishing. And then there's a different modules that want to maybe subscribe to the location, so they do that. And we do that through a middleware we call UWARP, which is DDS compatible. For those of you that know ROS, it's actually compatible with ROS, and I'm going to talk a little bit about that. Everything is parallelized and thread safe. We have great hardware support. I'm going to talk a little bit more in the next slides. There's support for custom builds, which is one of the biggest things here and something I wanted to talk to you about. Because we have hardware support, like, I don't know, think of this as one of the hardware. Okay, so we support this hardware, but we have variants of that hardware too. Maybe you want this version of the firmware that doesn't have this feature. We support that. And sometimes we even support it upstream, which means we have to test for this. We have more than 1 million of vehicles using PX4 right now. This is data that we surveyed from the companies that are within our memberships. But actually, we don't really know. It's impossible to know for the open source project because we are not charging for a license. We're not actually demanding from the companies that implement this that they share this info. But the members that are the companies doing Dronecode, some of them are manufacturers of the components. I'm 10 minutes over. Okay, good. So I'm going to go quicker. And we have 30,000 developers, like I said before. We got flight modes, which are providing a set of helpers to the developers to actually be able to do sort of autonomy. We have flight tasks that help the flight modes actually be able to control the behaviors. We have parameters where you can say, if you're going to take off a certain altitude always. Maybe you don't want to, every time you take off, set that. We have an events interface. If you're a developer, you want to make sure you can subscribe to things. And then we have control allocation, which translates the thrust and the torque. Like I was showing you, we support different geometries, so it will be hard for the developers that do the controllers to actually define and hard constrain the controllers to the geometry because we want to support multiple geometries. So we have a translation layer that helps you write the controller so that you don't have to think of the geometry, you think about it later. And we also support ROS2. This is an example of the hardware. This is a PixHawk. This is one of the projects that I was telling you about. We support more than 80 boards, and we have more than 100 sensors that we support within all the hardware collections. Mostly the architectures are STM32 based, IMX, and RISC-V. But we also support payloads, gimbals, batteries, debuggers. There's a whole ecosystem that is just doing this. And like I said, the mission planning software, it's also part of the ecosystem, something that we also have to test. We have the ROS to support thanks to the middleware. I'm gonna gloss through this because we're running out of time. We also have a simulation engine based on Gazebo, also based on Open Robotics projects. which allows developers to actually do very advanced things and test them. But how do we actually test it? And sorry that I took half of the talk for this. In my mind, it's going to be 5 minutes. So developer testing, I separated these two things. Unit test, integration test with simulation test, hardware in the loop test. Okay, that's what we can do in the cloud. Can be run in CI. But what about this? Flushing and installing on the hardware. Setting up the hardware, setting up the parameters. How do you want to tune this? Actually flying with an RC. Or maybe flying a mission, autonomous mission. And how do you validate that those missions and those controlling those flights actually work? So we do two different things here. Testing the test in the cloud, or mostly in the cloud, because we also do hardware in the loop. Let's run with the unit testing. So, unfortunately, our unit test coverage is less than 60%. Less than 60%. Why? Because it's been really hard for us to enforce this. We've been slowly building and growing this number, but it's really, really, really slow. It's very hard to incentivize the contributors right now to get this. But we do have them, and we do run them. The tests run in about 7 minutes per pull request, and we have about, I don't know, like 10 to 20 pull requests per day. So sometimes in a given Monday, I would wake up, go to my computer, and we would have like 50 pull requests that came in on Monday. Because, I don't know, developers worked over the weekend and just submitted the pull request on Monday. And surprise, everything in there was running on GitHub Actions and the runners from GitHub, which meant that a pull request was sitting in queue for hours, sometimes days. Because the collection of every test we did just took hours. So this is an example right now. This is the current setup, and this is just only taking 7 minutes. We do integration tests. This is a bit more complex. This is actually 3-step. We have a test runner, which is a Python script, and we have different tests. These are just some examples, but we have way more. And each one of those actually launches PX4 from zero, from scratch. And then PX4 launches Gazebo from scratch for each one of those, which meant that at least you have 5 minutes wasted in there in setting up the environment. And then you run the tests, and the tests took like 20 minutes each. We fixed that setup. Actually, I fixed that last October. And then we realized that when we fixed the execution time, we found out that there was actually tests in there that were failing because there were real errors. But we couldn't see them because there were timeouts in the execution, because sometimes when the test runner launched, it tried to launch PX4, and for whatever reason, the resources in the system were lost, or maybe it didn't actually launch PX4, so there was a timeout, but you didn't know about the timeout until like it was too late, like 60 minutes late. So we had so many failures, and we didn't actually know because we didn't have the observability into those issues. So I took it to the task, I tried to fix those issues, and then I found way more. These are just the only tests that sometimes fail intermittently, and we haven't figured out why yet. Thank you. I'm almost done. This is just an example of what's happening actual. This is from the screenshot from last night. 15 minutes execution time overall for all of the tests. It was a huge effort, but mostly it was me scratching my head against GitHub runners, because I actually didn't know how they worked. And the whole setup was, to me, honestly, something that I never dealt with. And then finally, we do hardware in the loop, and we do this through Jenkins, because one of the maintainers in his house has a test rack with a USB hub, with a bunch of FTDI to USB cables connected to all of the hardware. And every pull request, guess what? All the hardware got flashed. All the firmware got flashed, and then you configure everything, and then you check the status, and then you reset devices, and then you run tests for everything. This used to take hours too, per pull request. It was crazy. It was crazy. Like, why did we think this was a good solution? Because we didn't have anything. We wanted to have something, and we had to start somewhere. The honest reality is that we shut this down last month because, again, the hardware, first of all, we didn't have every hardware that we support. We only had the ones that the manufacturers shipped us, or the ones that we could afford. And second, we had a lot of timeouts too. When we tried to flash, sometimes the FTDI drivers didn't work. I don't know why. It was a Windows machine, and then we switched to a Ubuntu machine. We had driver issues. We had to reconfigure Jenkins. It just was a nightmare. We couldn't support it. As a maintainer, we had to spend more time reviewing the pull request than actually fixing this infrastructure, so we decided to turn it off. So if anyone here wants to pitch in, thank you. I would please talk to me. All right, so lastly, the most complex thing of all, how do we actually do builds? How do we publish artifacts? So our primary development environment is Ubuntu, whatever the LTS is. Right now it's 2404. We build using GCC, but since we do embed it, we have to use the ARM cross-build GCC version, and we're locked down to version 9 right now because of historical reasons. I'm actually working in trying to push that to, I think, 13. I don't remember which one it is. But we have a script that installs all the dependencies. Actually, we have that running in CI, and we know that if you want to run the PX4, we guarantee that if you run ubuntu.sh on a fresh machine, it's going to work because we have it in CI. Finally, we didn't have that beginning of last year. So this is how you run it. Make PX4 and then the variant of the hardware. So you always need to specify which hardware. So how do we make it so that we actually build all of the 80 hardware boards that we support? Well, we used to have a hard-coded file in which if you add a new support, you also have to make sure that you add that line and make sure that the string name is right. What happened was that sometimes the manufacturers forgot to add it there, and then someone reported an issue, and guess what? It wasn't in CI, so we never catched it. All right, that's an issue. Second issue, it took so much time to run everything because we were running a matrix in GitHub Actions, which meant that it was every pull request was launching 80 runners. So if you have 10 pull requests in queue, that means 10 plus 80, how much is it? 800. And each one of those took 15 to 20 minutes. That was impossible for us. So we created a Python script, and we actually grouped together by manufacturer, and we started caching those builds. And that made it so that if you're using the same manufacturer, sometimes the dependencies when you're making the build are the same. So you could save like up to 80% of your time on builds. So we wrote this script, and we put it on GitHub, and we trim it down from 80 to 23 jobs, so we only now have 23 runners. We also did something else, which is we moved into self-hosted runners in AWS using a platform called RunsOn. You have never heard of RunsOn. They make it so easy for you to actually run your own infrastructure. I'm really happy. And it's free for open source, so if you really want to try it out, it's really easy. So this is one group. Not XPX40, and it's like all of the different versions. This is V6X. All of these is the same hardware, but these are different variants. And this is the part that was actually killing us. But thanks to the caching, thanks to the new runners, like look, 58 seconds in running one build. It took 10 minutes at least before. Now it's taking a minute. So as a result, what took hours now takes 16 minutes. But still, it's a lot. Here's an example from pull request from last night. Lastly, 57 checks. I didn't talk about all of the things we do in CI. We have about 57 different checks. And an example, the container build failed because I wanted to be smart, and I wanted to push every container built into the GitHub registry. So I was doing a DDoS attack onto my API token, and I was basically running through the threshold in like the first hours of the day, which meant that from there on, throughout the day, every PR is going to fail. So this is still out there. So if you want to contribute something, that's a really easy fix. And I'm sadly not going to be able to do the human in the loop test, but we actually have a flight test team, and they do actually do the testing. And they submit logs through the website that we have, which is called PX4 Log Review. You do upload the logs. They give you nice charts. You know what happens. And then the developers actually tell you, oh, your motor is not aligned. This is why you have so much vibration. Maybe this is why you're not be able to move drone the direction you want. As a conclusion, my friends, testing in robotics is tremendously hard. My robotics colleagues here is not going to let me lie. We've been suffering and we need your help. So if you're ever thinking of collaborating with our robotics project, I know the few. Tomorrow we have a devroom. In which building, Kim? Is it UB? UB21 something. It starts at midday and there's really cool content. So if you have time, please go there. And thank you so much.